Hello everyone, and welcome back to the Cedille Cast. In this month's video, we interrupt the sequence on the generic derivation of induction for lambda-encoded types to announce the release of Cedille 1.1, which includes syntax for declaring inductive data types and defining functions over them using case analysis and recursion. This is no April Fool's joke. Cedille's core theory has not been extended with primitives for inductive data types, but rather, the syntax for inductive definitions and recursive functions in Cedille 1.1 is elaborated to pure lambda expressions in Cedille's core theory, CDLE. This is all thanks to the developments for generically deriving induction in CDLE, which we will continue to see in the next video. First, we'll see a basic example of an inductive definition, nat for natural numbers, and some functions defined over it. Data types are introduced with the keyword data, the name for the data type we're declaring, its kind, and a list of constructors, here too, associated with their type signatures. To define a function over nat by case analysis, we use the mu prime operator. Here's an example of it used to define predecessor for natural numbers. Mu prime takes a scrutiny in and a case tree associating constructor patterns 0 and second prime with a series of expressions. In the 0 case, we return the original argument in. In the successor case, we have subdata in prime, and this is the value that we return. We can also make recursive definitions with the mu operator. We'll use mu to define addition for natural numbers. In add, mu binds the name addIn as the recursive function being defined over the scrutiny m. AddIn is then available within the case branch expressions to make additional recursive calls with. Here, it's used in the successor case to add in to m and then increment. Before moving on to show examples of index types and proofs by induction, I want to re-emphasize that everything above is high-level syntax for data types and functions already derivable in CDLE. And I can even prove this by showing to you the elaborated terms. When Cedille is in navigation mode, and you press capital E, you'll be prompted with the elaboration command asking for a subdirectory to put elaborated files to. Here I'll just say elab. I now see open up a DIRD mode buffer with the list of elaborated files, here just one. Notice that the file extension is CDLE instead of CED, which is the normal Cedille file extension. CDLE files are checked with a separate tool that comes bundled with Cedille called Cedille Core. If I press Alt-S, Cedille Core reports back that this file type checks. Of course, if I were interested in seeing more details about the definitions in this file, for small enough CDLE files, I can kick in Cedille mode and then type check this. Due to limitations in our Emacs front end, these large files often can't be checked by Cedille mode, but in this particular case, if I make the switch, type check, and edit out the long wait, then we can see the elaborated file is also valid Cedille. And scrolling towards the bottom can begin to see the translation of nat, pred, and add. The definitions at the beginning of the file are from the generic derivation of induction, which we'll be covering in later videos. Returning back to our example, here is the classic vector type defined showing off parameterized and indexed types. Notice that within the constructor type signatures, the data type vec is not written as applied to parameters, only its indices. The type A really is a parameter to the definition. It is not allowed to vary in recursive subdata. With the definitions we have so far, we can of course define the append function for vectors that provably returns a vector whose length is the sum of the lengths of the input vectors. We will complete this function with a mu expression recursing over argument x's. Due to limitations in type inference, we must give the motive for induction explicitly, so that in each case our expected return type reflects the shape of the indices and the scrutiny given for each pattern. The motive is given explicitly with the at syntax. As is usual, in the v-nil case, the expected type is vec a add 0 in, which is convertible with the type vec a in of y's. In the vcons case, the length im of our tail is bound in an erased pattern, because vcons takes an erased length argument, and the head and tail are bound unerased. Finish off the definition. To finish off the definition, we cons the head of our vector x's with the result of appending y's to the tail of x's. At this point, everything we've seen so far has been fairly standard stuff, with lower level facilities for case analysis and recursion than found in languages like Agda or Idris. The next set of definitions will show a more exotic feature of Cedille's data type system, its semantic termination checker. We will demonstrate this by showing how to define division over natural numbers in Cedille in a way that Cedille recognizes as terminating. In order to do this, the first thing we have to notice is that our declaration of type nat also introduces some additional global names. These can be seen by selecting the span corresponding to the declaration and opening the inspect buffer. What you see here is a type family is nat, a family of mapping types to types. A member of that type family, little is nat, of type big is nat, and a type coercion function to nat that says for any type x in the type family is nat, we have a way of converting terms of type x to terms of the type nat. Similar definitions are exported for each declared data type, including for vector. These definitions are part of Cedille's semantic or type-based termination checker. To give an example of how these global definitions are used, let us define predecessor for nat in a way that expresses that it produces a value no larger than its input. Instead of being defined over the concrete nat type, here pred prime is polymorphic over any type in the family, in the type family is nat. Here, with our facilities for pattern matching U prime, we must explicitly give the witness is, asserting that the type in is in the type family is nat, to mu prime using this angle bracket syntax. This allows us to pattern match on the scrutiny in as if it had type nat. Crucially, if we look at the context in this the successor case, what we'll notice is that pattern matching in this form preserves the type of the scrutiny. The subdata in prime also has type in. It would be type incorrect to, say, return an expression such as successor in. And the type error that we get is twofold. One, that successor expects a term of type nat, and it's given a term of type in. But more importantly, that the expression successor in is expected to have a type nat. It synthesizes type nat, but the return type for this expression should be this abstract type in. Reading these types parametrically, what we can see from the type signature of pred prime is that the only thing that you can do with an arbitrary element of type in the type family is nat is either to cast it back to nat using the coercion function to nat, now this sub-expression is fine, but still the larger expression is type incorrect. we can either coerce a term of type in the type family isNat back to the type nat, or perform case analysis on it. Thus, the only way to return an expression with the type in is by returning the argument of type in directly, or by performing some number of pattern matches and then returning some data revealed by that. In predecessor, we only analyze one case, but we can in general do arbitrary case analysis in an abstract type preserving way. Consider the definition of minus. The first numeric argument to minus has type in, where in is a type in the type family isNat. The second argument has the concrete type nat. Reading the type signature parametrically, we again see that minus prime must either return its first real number argument or some arbitrary predecessor of it, perhaps computed using the second argument. In the 0 case, if we want to compute what m minus 0 is, that's simply m. In the successor case, we take the predecessor, rewriting the witness explicitly as providing the witness as an erased argument, the predecessor of again, see here that the expression m minus n has this abstract type in, and the type family isNat. Our type preserving, our predecessor we defined before, preserves this type, so the type of the entire expression is in as required. We need just a little bit more kit to define division. Let us introduce booleans, if then else, and then a less than comparator for nat. So far, so good. Just to reiterate the perhaps unfamiliar syntax, for defining if then else, we take a boolean, an expression to return in the true case and an expression to return in the false case, perform pattern matching on that boolean. When it's true, return the then branch. When it's false, return the else branch. To define our less than comparator for nat, we will first want a version of subtraction where this polymorphic in the type family isNat is instantiated to just be the ordinary nat. This we can define in a straightforward way. Recall that this lowercase is/nat is the witness that nat is in the type family is nat. What we get from this definition is the fact that, by definition, our abstract type preserving minus prime, which we find here, and our ordinary minus defined in terms of minus prime are equal by definition. Thanks to Cedille's erasure semantics. With this, we can define LT. We will do case analysis on the result of subtracting from successor m in if after subtracting n from successor m we still get 0, then m must have been smaller than n. Otherwise it was not. Now, with everything above, we can show how to define division by iterative subtraction in Cedille in a provably terminating way. We begin by recursing over the dividend m if our dividend is 0, then 0 divided by any number n should be 0. If our dividend is the successor of some number, we first want to test whether that successor m is less than the divisor. But as we saw, successor m is not a well-typed expression. At the moment, Cedille requires that if you want to use the subdata of a mu pattern, such as m, as if it had the concrete data type, nat, you must explicitly cast using the conversion function exported by the data type. Here we make a let definition for that coercion. What's going on here? Well, while data type declarations introduce global definitions for termination checking, recursive mu expressions introduce local definitions for termination checking. The names given to them are derived from the names of the recursive expression. For example, for the mu expression here defining divin, we have type slash divin, or type divin, the type of expressions for which it is legal to make recursive calls on. A local witness is type divin, which is a proof that our abstract type here, type divin, is in the isNat type family. That is, that it can be used for pattern matching as if it had type nat. And finally, divin, our inductive hypothesis. Note that it expects arguments of the abstract type, not of the concrete type. This way, we can be sure that all invocations of divin are done on expressions that are smaller than the original pattern. After the type coercion, we can compare the dividend and divisor, and if the former is smaller, return 0. Otherwise, we want to subtract the divisor from the dividend and divide the result by n and add 1. If we were to use the version of minus defined for regular numbers, we would get a type error. The expected type of arguments for div_in should be type div_in, but of course the synthesized type of this expression is nat. In languages using syntactic termination checkers, that syntactic checker would also complain about this expression. The recursive function div_in is given an argument, some expression that is not obviously smaller than the original pattern. For those checkers, typically the only allowable expressions that concur here as a recursive argument is subdata that is bound by some constructor pattern. For Cedille's termination checker, we just need an expression that preserves the abstract type of the types of subdata. With our type preserving minus, the whole expression type checks. Minus prime expects a number of the abstract type div_in, and an argument to subtract it by, and return something of that abstract type, precisely as expected by the recursive function div_in. That concludes this video. Hope you enjoyed it. If you're interested in more about data types in Cedille, check out the release page on our GitHub and the language overview directory in the Cedille source. In the next video, we will continue covering the generic derivation of induction for lambda terms done in pure CDLE that makes data types in Cedille possible. Hope to see you then.